Okay, so this is a review for the Solutions unit. Before we get started, I suggest that you get out your reference tables. We'll be using tables F, G, and T, which is the formulas table. And you will need a calculator, something to write with, and some scrap paper in case you want to solve some problems as we go along. This will be in two parts. I'm going to stop it halfway through, upload it, and then record the second half. Feel free to pause me when we get to a problem, try to solve it on your own, and then check for the correct answer. So let's review. First of all, solution is a homogeneous mixture of substances in the same physical state. So this homogeneous mixture can contain atoms, ions, or molecules of one substance spread uniformly throughout a second substance. Remember, homogeneous means consistent throughout. So when salt is stirred into water, the individual Na plus and Cl ions separate and uniformly spread throughout the water, forming a solution. So it appears to be one substance. Now that substance can be clear or it can be colored. You can also have a solid solution. One solid may be dissolved in another. In this case, you have zinc and copper. This was an example of a substitutional alloy where some of the zinc molecules replaced the copper. Brass is a solution of zinc and copper. So when metals are mixed together to form a solution, the result is called an alloy. You can also have a gaseous solution. For example, air. Air is a mixture of gases that form a solution. Even though air is only 20% oxygen and 79% nitrogen and then 1% of a mixture of other gases, those gases are completely spread evenly throughout the entire solution. It's consistent throughout. Now, for the most part in this unit, we're talking about a solute or a solid dissolved in another liquid when we talk about a solution. So, just to recap, a solution is a homogeneous mixture, meaning it's consistent throughout. It's made up of two or more substances. And the two parts of the solution are the solute and the solvent. The solute is the thing being dissolved, or the substance being dissolved, like salt or sugar, that dissolves in a solvent like water. A solvent is usually a liquid, and for most examples in our class, water. Sometimes it can be something else, like alcohol or hexane, but for the most part we use water. So when we have a solution in which the solvent is water, we call that aqueous, AQ. A precipitate is a substance that is caused to become insoluble by either heating or just by chemical reaction. I mix two things together and one settles to the bottom of the solution. Now, we can use a very simple example like salt and water. Salt dissolves in water, it looks uniform, but then if I boil it to evaporate the water, the salt that remains is a precipitate because it's what's left over. Solubility is the most substance, the most amount of grams that can dissolve in the water or solvent at a specific temperature. And we use table G to determine this. So what happens during the process of dissolving? Well, the solvent molecules have enough attraction for the solute particles to break the intermolecular forces between the solute particles. For example, you know that water is polar. The hydrogen side of the water molecule is positively charged, while the oxygen side of the water molecule is negatively charged. This is because oxygen has a higher electronegativity than hydrogen. So when I put salt in water and I stir, the solvent, meaning the water molecules, surround the salt, and the oxygen, which is the negative side of the water molecule, becomes very attracted to the positive sodium ions, while the hydrogen side of the water molecule becomes very attractive to the chlorine, the negative chlorine ions. So when the solvent particles are attracted to the solute particles, they wind up bringing the solute into solution, and it dissolves, and it appears, as it does here on the right, as one clear solution. Now again, this could be colored as well. So what are some factors that can affect the rate of dissolving? Well, for one, we have surface area. Remember, the greater the surface area, the faster the substance will dissolve. And when I say greater surface area, I mean smaller particle size. For example, if I have a cup of water and I have a sugar cube and I have granulated sugar, the sugar cube will dissolve slower than the granulated sugar. Why? Well, the sugar cube has got smaller surface area, while the granulated sugar has a greater surface area. More solute particles can come in contact with the solvent and be pulled into solution. And there's my example. That's why granulated sugar will dissolve faster than a cube of sugar. Another one is stirring. You've all made a glass of iced tea or lemonade. When you increase stirring, it causes the substance to dissolve faster. Why? Because you're agitating the solution, and more solute particles can come in contact with the solvent and be pulled into solution. And lastly, temperature. For solids and liquids, increasing the temperature increases the rate of dissolving. This allows more solute particles to collide with the solute. Why? Because when you increase the temperature, particles are moving faster and they're colliding more. So the solute and the solvent are colliding, and thus the solute dissolves. This is not true for gases. When you increase the temperature of a gas, the rate of dissolving or solubility decreases. Because when you increase the temperature, gases start spreading out and colliding more, and they want to go away from one another. When you decrease the temperature of a gas, particles slow down, they come closer together, then we can get more particles into solution. This is why soda should be refrigerated and why it becomes flat if left out in the open. In the refrigerator, the gaseous carbon dioxide molecules are closer together and will stay in solution longer than if the soda is left open on a counter where it's warmer and the gas molecules collide and come out of solution and evaporate. And let's remember, like dissolves like. Polar only dissolves polar solutes will only dissolve in polar solvents, and ionic solutes dissolve in polar solvents. Nonpolar only dissolves nonpolar. So down here I have polar and polar. Here's the salt that I was telling you about, NaCl. Your Na is your plus lavender atoms. Your chlorine is your negative green atoms. And when you put them in water, notice how the positive hydrogen side snugs up against the negative chlorine, while the oxygen side, which is negative, snugs up against the sodium. And in B, you have nonpolar and polar. You can see what happens. There's no mixing. There's no dissolving. Like dissolves like. Let's move on to table G, our solubility curve. One thing to remember is that this only takes place, this table, in 100 grams of water. So you might have to make some adjustments if it's 200 grams or 50 grams. I want to draw your attention to the negative curves on the solubility chart. HCl, NH3, and SO2. These are gases because as temperature increases, solubility decreases. So the horizontal line in the graph shows temperature, and the vertical line shows how many grams of a solute is the most that can dissolve in 100 grams of water. The various compounds on the graph, the solutes, dissolve differently at different temperatures, and for a given temperature only a certain amount of the solutes can dissolve in 100 grams of water. Some of the solutes on the graph are in the solid form while others are in the gas form. Remember, this graph only represents the effect that temperature has on solubility. Solubility of a solid, KNO3, NaNO3, increases as temperature increases. So positive curve are solids, and as temperature increases, solubility increases. And as I said earlier, our negative curve are our gases, and as temperature increases, solubility decreases. With the solubility curves, there are some relative terms like concentrated and dilute. Concentrated just really means that a large amount of solute per given amount of solvent. So this is usually, when we say that something is concentrated, we usually say that something is supersaturated. Dilute means that there's a small amount of solute per given amount of solvent. So if something's dilute, that it is unsaturated. So that brings us to our three terms: saturated, unsaturated, and supersaturated. So a saturated solution contains the most amount of solute that can dissolve at a given temperature. If you added any more, the solute would not dissolve. When you graph the solubility of a solvent, the line on the graph represents saturated. So any data point that falls on a line is a saturated solution. So for example, if you have your table handy, I want you to look at 70 degrees, see where it intersects KNO3, and you should see that the maximum amount of salt that can dissolve in 100 grams of water is about 134 grams. So the line for saturated can only hold 134 grams of KNO3. Unsaturated means that it contains less solute than a saturated solution. I could still add more, stir it, and it would dissolve. Again, looking at your reference table at 70 degrees, see where it intersects KNO3. If you have 130 grams, this would be an unsaturated solution because KNO3 at 70 degrees is not saturated until it's about 134 grams. So if your data point is below the line in question, it's unsaturated. Supersaturated is very temporary and a very unstable state caused by slowly cooling a saturated solution. It has more solute than it can possibly hold. If you look at table G again at 70 degrees, if you have 137 grams of potassium nitrate, that would be considered supersaturated. That data point is above the KNO3 line, and if it were saturated, it would only have about 134 grams in it. Okay, I'm going to stop here and upload this and then record the second half.